So with that, I'd like to introduce the first speaker. And so Dr. Sergio Brinja is a professor and associate department head at the University of Massachusetts in Amherst. So his research includes design and behavior of reinforced concrete and precessed concrete structures, bridge field monitoring, and seismic retrofitting. He is an ACI, he's a member of the ACI subcommittees 318H, which is seismic provisions, ACI 318C, safety, serviceability, and analysis. He's also the chair of ACI 369F, which is a seismic retrofit, as well as a member of the subcommittee ACI 562, the repair code for seismic. And so with that, I'd like you to join me in welcoming Dr. Brinja.
Good afternoon, everyone. First, I'd like to thank the organizing committee for inviting me to participate in this important session. Welcome to the members from JCI. My name is Sergio Brinja, as was noted. This research, when I was invited to present at this session, this research was hot off the presses when a couple of years ago, but then the pandemic hit, so this seminar was pushed back a couple of conventions, but I'm very happy that we're able to present this in person today. I'd first like to acknowledge my graduate student who participated in this project, Jorge Rivera Cruz, who is now with the U.S. Army Corps of Engineers. He's stationed in Florida, but currently in Puerto Rico. An outline of presentation, I'll be going through some background and motivation for the research. Then I'll jump right into the specimen details that we tested. This is largely a presentation related to experimental testing and how those experimental tests help inform some of the changes that are being proposed for perimeter beams to provide integrity reinforcement. Then I'm going to, again, look at laboratory testing results, discuss those results, and come to some conclusions. So in terms of background, the primary objective of the research project was to evaluate the structural integrity provisions that exist in ACI 318-19, and these are for cast-in-place perimeter beams. The primary objective was to evaluate the placement of where bottom bar splices are located to provide continuity for these perimeter beams that are one of the fundamental aspects of detailing of this type of beams. But as an effect or as a consequence of some of the testing observations, we also endeavored into going into evaluating the transverse reinforcement requirements, particularly spacing of perimeter beams that are designed in seismic design categories A or B. And those are the lower seismic design categories in the United States. And this, again, as I mentioned, this was prompted by observations after the testing. We did not expect this to take place a priori before we started testing. And so that to frame the discussion, let me just give you a little bit of background and the intent for section 977 in ACI 318. And the idea of that section is to prevent disproportional collapse of large portions of the structure after a small failure or a failure of a small portion of the structure. And I quote ACI 318-977 that it is the intent of this section of the code to improve redundancy and ductility in structures so that resulting damage may be localized. The idea here is that after the unintended failure of an element due to some form of abnormal loading, this failure will not propagate to the rest of the structure and cause general collapse. Many of you know what that means. And what that implies, though, is that there's the ability, the structure has the ability to redistribute internal forces after local failure. And that this capacity is maintained at large displacements, so at large plastic deformation. So I'd like for those of you here to try to keep that in mind as we go through the presentation. So ability to redistribute forces and maintaining capacity at large displacements. Going over some of the details, this is borrowed from one of the ACI publications that summarizes the typical details of for integrity reinforcement in perimeter beams in ACI 318. The key aspects is that one needs to provide continuous top and bottom reinforcement, and there's a certain fraction of reinforcement that needs to extend into the supports. So 1/4 of the maximum reinforcement, or the reinforcement provided in the maximum positive region, needs to be extended into the supports, and 1/6 of the negative reinforcement at the support needs to be extended or be continuous through the length of the beam. And continuity may be achieved by splicing longitudinal bars, providing Class B splices, so they don't need to be literally one piece of reinforcement, they can be spliced. And the other aspect of integrity reinforcement is that these longitudinal bars, those bars that are intended for integrity, need to be enclosed need to be enclosed by either closed stirrups, so U stirrups with a cap tie, or hoops throughout the length of the beam. The spacing of these is not indicated in ACI, but it's presumed that the spacing would be resulting from other demands in those elements such as shear and torsion. So with that in mind, what we did, and I will look back at some testing that has people have conducted other researchers have conducted on structures in higher seismic design categories. But our intent was to evaluate how these provisions worked for buildings designed in the lower design categories in this country. So we chose this floor plan, which has been studied by others, essentially from NIST et al., Liu et al. From NIST. With the building was a rectangular, fairly regular rectangular building in which the perimeter frames are the ones that we are intending to study, and we modeled part of that perimeter frame, thinking of the potential loss of an intermediate support, and we would construct this H-shaped specimen at full scale in the laboratory and test it to failure. So we were using a building prototype to design our laboratory specimens. And this, what I intend to show you is just the details of the specimen and not the specific spacings and so on. But what we varied essentially, you see two cross sections here. These are the beam cross sections, including that arrangement of transverse reinforcement with a cap tie to provide a continuous reinforcement enclosing longitudinal bars that are intended for integrity reinforcement. And what we were intending to study was the location of this bottom splice in the bottom longitudinal reinforcement, which really would provide the catenary action that's needed to prevent disproportional collapse. I mean, some of these details rely on catenary action to prevent disproportional collapse from occurring. The details of the columns are not important, but what's really important is where we placed the lap splice here and the arrangement of these closed stirrups along the specimens. And as you can see, we tested 3 specimens. The dimensions I should highlight were full scale, so we had 40-foot long specimens. And the only thing that we changed in these specimens is where these bottom bar splices were located, centered about the center column, and some two distances away from the center. The idea was to minimize the congestion in the joint region and see if moving the splice out of the column region would affect the response of the specimens. Just a quick view of the specimen in the laboratory. The specimen was restrained both in plane and out of plane. And it's a fairly simple setup. We were loading here at increments of load to come up with the maximum load that this specimen could take and try to develop that catenary action that we were looking for to prevent disproportional collapse. And some of the instrumentation that I will be referring, the specimens were instrumented with displacement transducers along the length of the span. We also had inclinometers located at the ends of the beams to measure rotations and come up with moment rotation relationships. And we also had load cells located here under the application of the vertical load. And we also wanted to measure how much restraint was being provided at the top and bottom of the column. So we placed some load cells also at the ends. One item that I will not discuss in this presentation is we also instrumented longitudinal bars with strain gauges at the location shown here to address whether, in fact, the location of lap splice was going to be influential in the specimen response. So I'm going to go through a series of slides, just show you the general behavioral trends, specimen by specimen. I started with a load deflection curve, some crack patterns here on the right, and then I'll show you some pictures. And you will see that each specimen, all the specimens had similar behavior, as you will see. The typical characteristics of the loading protocol was we would load the specimens up to cracking, unload, and then load to peak load, and then all these drops just correspond to load holds so that we could mark cracks. So specimens reached a peak force and then gradually unloaded until suddenly there was a drop in force at some displacement between 10 and 15 inches and with some residual capacity. So what's going to be important is what caused this sudden drop in load, and try to address that with what other people have tested and found in similar tests. And the development of cracks is shown here on the right for those three loading steps, I guess. 30 kips, 52 kips, and 28 kips. And as you can see, marked in darker color are the critical cracks that were forming in those specimens as they were developing plastic hinges towards the end at increased values of load. So you can see here at the 52 kip load, we had bottom cracks forming vertically, flexural cracks, and there were two diagonal cracks that started forming towards the end of the specimens, not right at the face, at the beam column face, but some distance into the span of those beams. And to give you an idea, this is just the stage, the cracking stage at ultimate load, at the residual load, and you see the type of crack that we saw at the end. It's a pretty wide crack that formed. There was crushing in the concrete at these large displacements we were experiencing, and eventually one of these cracks towards the end of the beam, depending on the specimen, was the one that limited capacity. Specimen 2 had a similar behavior, loading to peak and then sudden unloading. In this specimen, we kept loading to try to develop, as I will call later, catenary behavior of the specimens. You see similar crack patterns as for specimen 1. And again, you can see an overall view of how much deflection was imposed on the specimen. And the critical crack in this case formed in the south face. And this gives you an idea of the width of that critical crack. And in this case in particular, we were fracturing stirrups as well. And specimen 3 had similar behavior, the sudden drop in load, some increase in load after this first sudden drop, and then we eventually had another fracture occurring here. So what was interesting to us was that when we explored in the literature, this type of curve was not observed in previous specimens that were tested that were similar to these, but designed for other design categories. Notice this big crack. This is not after moving the specimen. This is right after testing. So it's a huge crack that forms, that it starts diagonally and then suddenly widens as the stirrups fracture. So if we superimpose the 3 tests and also the results of the 3 tests with models that people have proposed and some analytical studies we did as part of this research, the 3 specimens, what's important here is you can see a comparison of their the load deflection response. These stars indicate the sudden load drop that corresponded to the widening of those diagonal cracks that I just pointed out prior to stirrup fracture. We were then expecting to, if we look at models like the one dashed here that I'll discuss in a few slides, what was expected was a drop in force as those diagonal cracks widen, and then the development of catenary action that would carry the specimen onto higher loads and prevent disproportional collapse. That did not happen in our specimens after first drop. There were other things that were happening, such as stirrup fracture, that prevented that catenary behavior from developing. In order to study whether our specimens would be able to develop this catenary action, we did a model in SAP 2000. Many of you know that program, where we used some moment rotation relationships to try to develop these unloading branch and then onto catenary behavior. So we did nonlinear analysis to try to simulate the response of the specimens. And for that model, what we employed was this moment curvature relation, where the big unknown here, this was done by calculation, looking at the cross-section and measured material properties. But what we didn't know was the residual capacity and how quickly the beams would unload. So we just assumed some properties to try to get the catenary behavior to develop. So this model does not include any fracture or loss of shear transfer in order for us to be able to, going back to this plot, to be able this curve that increases with increased deformation. So going to what other people had tested, I think I mentioned the study by Liu et al. As you can see, their specimen looked very similar to the one we tested. The key difference here was that these specimens were detailed for intermediate moment, were detailed in accordance with intermediate moment frames or special moment frames. So these would be for seismic design categories 3C through F. And the key difference is the amount of longitudinal reinforcement at the ends, but also the spacing of transverse reinforcement. And as you can see from at the ends of the beams, as you can see from the plots down here, they measured load deflection responses that were very different from the ones we saw in our testing. So in their tests, they were able to develop peak force, then some unloading as the force transfer changes from beam behavior to catenary behavior, and then catenary behavior at larger displacement. And they found the same type of behavior for the two specimens they tested in this program. The load transfer characteristics, they categorized it in 3 stages. What some other people have called beam behavior, they said, well, this is more in the first stage of loading, beyond peak and first unloading. There's an arch that forms between the application of force and going into the supporting columns. And then as you keep increasing deformation, this compressive zone narrows and narrows until you're able to develop this catenary force that allows the specimens to pick up force by catenary action, by cable action. Other people have studied this problem as well, and they have proposed simplified models to try to capture the response of specimens like this. In tests by Zhang and Zheng, you can see here that they also identified what they referred to as a beam stage, a transient stage, and a catenary stage, and they tried to define each of these stages through a series of multiple lines, depending on displacement. They proposed a series of equations to capture the response. And then they superposed. What they did is using their model, they tried to replicate the response that was measured by Liu et al. So what's interesting is that these curves lie right on top or are very close to the curves from the measured test from Liu et al. But this is the model that we also used that was shown as dashed in the load deflection response that I showed earlier, which is right here. You can see that their model was not able to predict the response of the specimens we tested in this program. Our specimens were deflecting much more, and more importantly, we're not able to pick up the force that is associated with catenary behavior. So this is where what I mentioned earlier was that the characteristic of our specimens was quite different from those that had been tested previously, primarily in that there was a sudden crack widening at some level of displacement, and I think more importantly, the fact that as the crack widened, eventually there were stirrups that fractured. So we thought of, what was the cause of first this sudden drop in shear force, and that would then translate or lead into fracture of stirrups. So we wanted to investigate what generated this loss in shear force, sudden loss in shear force. And for that, we had to incorporate the two. So we evaluated we used the ACI equations for shear strength, where nominal strength is given as a summation of the concrete and shear stirrup contribution to shear strength. We looked at the 2 code equations from ACI, but we also looked at models that have been proposed in the past that actually incorporate the effect of plastic rotation in reduction of this VC term. So 2 models that we studied. The important aspect here is this gamma term that indicates that the gamma or shear strength, concrete contribution to shear strength, decreases with increased rotational demand. So using these 2 models, we were trying to replicate or understand why our specimens failed the way they did. And if we, so this plot is kind of, there's a lot of information going in this plot. These are the 2 ACI code equations, the one with no size effect, the one with size effect. Size effect equation is right here on the right. And then also shown here is a plot of the shear force associated with plastic hinging of those specimens. So our specimens were able to reach that shear force associated to plastic hinging, but at some point at increased rotational demands, we saw a drop in shear force. And that could be explained by using those models that incorporate reduction in shear strength with rotational demand. And as you can see, we were able to identify a range of values or rotational demand values for which we would expect the V sub C term to drop suddenly, which might explain the behavior of our specimens. So using the instrumentation in those specimens, along with this simplified plastic model, we were able to find, and I would just like you to focus on these values right here, we were able to find that for the 3 specimens we tested, the anticipated normalized rotational demand went from about 8 to about 17, which matches well with this range of values that is shown here as the intercepts x, y with the plastic curve, which leads to explaining why we had this sudden drop in shear strength at higher rotational demands. Now, this doesn't happen in specimens or elements that are detailed according to high seismic design categories because of the closer spacing of stirrups that prevent widening of those diagonal cracks. So in conclusion, what we concluded is that I didn't mention anything about longitudinal bar splice location because there was no influence in the behavior of those specimens on the 3 locations for that bottom longitudinal splice location. But we did find, though, that catenary behavior, which leads to prevention of disproportional collapse, did not develop because the specimens did not have the capacity to carry loads beyond formation of these critical diagonal cracks, and therefore the specimens failed prematurely in shear prior to being able to develop that catenary action. And we recommended, or so we found that models that do include reduction in shear strength, V sub C, as a function of rotational demand can be used to explain this type of behavior. So the steep diagonal crack that formed after loss of VC was really decreased the available shear strength, which then led to eventual fracture of transverse reinforcement in some cases. So these are the main findings of this study. I think what follows is that we need to provide attention to how we detail these beams so that they don't suffer from these sudden losses in concrete contribution to shear strength as a function of rotational demand. So I would just like to end with a series of acknowledgments for people or organizations that provided support for this research. And with that, I'd like to stop and ask you if there's any questions. I don't know how you want to moderate questions. Okay.
We have a couple minutes for questions if anybody would like to step up to the mic here, kind of difficultly placed behind the column. Yeah. Yeah.
I might have missed it. So when you show the special moment frame specimens, I saw a fixity in the columns in terms of foundation. Was that replicated in your specimen? I don't know if I saw it correctly.
That's a good point. Our specimens, the boundary conditions at the base were pinned.
Pinned, yeah.
So what we were trying to model, if you remember the frame, we're trying to model from approximately mid-story height to mid-story height, where there's very little moment. I don't know what the motivation was for fixing the bases in those other columns that Liu et al. Tested.
Oh, thank you.
So how about the top of the columns? How did you fix the top of the column?
We also had pins and we had steel braces going backwards. So the top of the columns were also permitted to rotate, but they were restrained laterally in plane.
Sergio, you didn't mention the very much about the location of where that hinge formed. Did that correspond to where the spacing of the stirrups changed, or what? Because it doesn't seem to be in sort of the natural position.
Yeah, you're probably, I didn't mention it at all, Roberto, thank you for that question. It was farther into the span. In our specimens, the spacing was constant because of the demands along the length of those beams, but the diagonal cracks that I showed you before initiated at the point of termination of bars extending from the column into the span. So that was the triggering fact that initiated those cracks. The widening of them had more to do with constant spacing of stirrups, yeah.
I guess I'll ask one. Do you have any plans to do any subsequent research, looking at the shear spacing, essentially for something that's not an intermediate or special moment frame?
Sure.
Include that?
I mean, if there's, academics in the room laugh because we're always happy to do tests. It's just a matter of money.
Yeah, sure.
Those specimens are really expensive to build and test. I mean, they're big, heavy specimens, yeah. I mean, we would be definitely interested in doing that. Hopefully, at some point, we will be able to do so.